scatter plots relate two different sets of data, two variables, not just one. This is called bivariate data, means bi is two, right? And it's showing us the relationship between two different pieces of data. Let's try a really pretty clear example. I want to see the relationship between, I have data on people, I have their age, which I will put along the x-axis, and their height, which I will put along the y-axis. So it's pretty clear that, say, somebody who's 1 year old, I might have someone this height. I'm not going to give values to the height. I'm just trying to get across the idea here. Somebody that height, somebody that height, somebody that height, all these different ages. And as they get older, in general, their height is going to increase. I think that's pretty clear. Now, you might have somebody who's kind of old, 10, that's not old, but old, right? Who's very small. And you might have somebody who's kind of young, but happens to be kind of tall for their age. Those might be outliers. But what we're doing here is we're plotting a bunch of little data points. And once we get the data points there, we are trying to visualize a line that comes closest to most of the data points. It doesn't have to hit every data point. In fact, it's almost impossible for it to hit every data point. We're just trying to find the line that is closest to as many of the data points as possible. And once we find that line, well, then we can describe the scatter plot meaning all these little red dots, and we use three ways to describe it. We describe a scatter plot by talking about its direction, its form, and its strength. So direction, think about it just like from algebra, or pre-algebra for that matter. This green line that I drew is going in a positive direction. So in this case here, the direction is positive. In fact, the only directions that we have when we're analyzing a scatter plot are positive, negative. I guess you could have one that's totally, that's perfectly horizontal, but that's very unlikely that you would have one that was perfectly horizontal, in addition to which that's kind of boring. The form. Well, in this case here, I can draw a green line that is linear. Sometimes I would get a scatter plot. If I plot different points, I might get a scatter plot that looks something like that. Well, if I draw the line that's kind of going closest to most of those points, well, that's going to be a curve that is non-linear. So it's either going to be linear or non-linear. This one here happens to be linear. And then the strength. At this point in time, that is really kind of a matter of judgment. And in this case here, I'd say that looks pretty strong. I mean, if you said that this relationship between age and height was weak, I would have to say you were wrong. If you said it's moderately strong, that's okay. Right now, I'm just using an adjective, and in a couple minutes, we'll talk about what numbers we use to calculate the strength. So this would be a positive, linear, strong relationship. And in the worksheet, they gave us an example very similar to the one that I just picked out. They're looking at heights of, average height of girls at different ages, and they also went 2 through 10, and they did it height in inches. Now, it is very important to make sure you know which piece of data goes on the x-axis and which piece of data goes on the y-axis. And the best way to think about it in my mind is that the x-axis is your independent variable. It's your input. Your y-axis is dependent on the x-axis. That's your output. Now, in statistics, you're not really going to have necessarily a cause and effect relationship. But you're trying to think logically. It's clear that you would put in a girl's age to get an estimate of how tall they are. You wouldn't put in the height to get an estimate of how old they are. It's the age of the girl that kind of determines the height. The height is dependent, for the most part, on the age. So the x-axis is going to be independent, and the y-axis is going to be dependent. The x-axis is my input value, and the y-axis is my output value. If it is not clear which is which, then it won't matter. But most of the time you'll find that one of the variables is kind of the independent and the other one is kind of the dependent variable. So here they have graphed this data, and they've drawn a line that looks pretty much like a line of best fit. It looks like the line kind of fits most of the data points. In fact, in this particular case, this is positive, it is very linear, and it is very strong. It's a very strong positive linear relationship. So I have the line, and my problem is, well, what's the equation of that line? And really, why do I care? Well, the reason I care is because if I can get a strong positive linear relationship here, then I can use that to make predictions. I can say, well, my data ended right here, but I can make a prediction of how tall I think a 14-year-old girl is going to be. So linear relationships enable us to use these predictions, make estimates. It's not solid, because obviously if I went out here to somebody who's 80 years old, well, this data will tend to start going down. People start to shrink. So the linear relationship doesn't hold for all ages, but I would say it's probably likely that it does hold in the growth ages from, say, 0 to 14 for girls, that it's probably very linear. So I want to find the equation. Well, the equation of a line, if you remember, is y equals mx plus b. The m is the slope. The b is the y-intercept. We already know that y is our height, and x is our age. So really, this would be nice to write as height equals m times age plus some constant. Well, how can I find my slope? I can find my slope just like I would find the slope of any line. I write a line and I can see slope is rise over run. It's delta y, the change in y, over the change in x. And I can see with my line, well, it looks to me like I am going up. So I'm going to do a different color here. From this point here to that point there, I have a rise of 10 and a run of 4. So my slope is 2.5. And that's exactly what they calculated here using some different numbers. My y-intercept was 30. So the slope of this line, the equation for this prediction of relationships, would be predicted height is equal to 2.5 times the age plus 30. This is height in inches. So if I want to now predict how tall is a 14-year-old girl going to be, the height is equal to 2.5 times 14, that's the age, plus 30. Well, if I do this multiplication and addition, it comes out to be 65 inches. So you can see how this is a very valuable linear predictions are a very valuable tool. So now, what do you think? I'm going to show you how to do it on the calculator, because this is a statistical problem. Much easier to do on the calculator. And it's going to give us an additional piece of very important information, which is the correlation. So let's do it on the calculator. I'm going to go stat, and I need to enter the data into the calculator. So in this case here, I'm going to use L1. I'm going to clear it, and that's going to be my age, my x variable, and L2 is going to be my height. I'm going to clear that. That's going to be my height. So I'm going to enter in the data. So I'm going to go, my ages are 2, enter, 3, enter, 4, 5, 6, 7, 8, 9, and 10. Very convenient, had all these nice ages that are integers from one another. Now the height, 34, 37, 40, 42, 45, 48, 50, 52, and 54. Now, if you're watching, you probably saw that instead of doing 52, I made a mistake, and I typed in 62. How do I fix that? Really simple. I just go right up to 62. It's highlighted. Down here it is saying, in list 2, item number 8 is 62. I'm just going to type 52. And it changes it. So no problem changing pieces of data. So I have the data in there. And what I want to do now is make a linear regression. So I'm going to press stat. I don't want to add any data. I want to do some calculations. And if I look down here at number 4, it says linreg, linear regression. And it says, well, linreg, AX plus B. I'm sorry that the stats calculator uses different letters. I wish they used M. But A is the same thing as M. So I want to do a linear regression. That's number 4. And I want to do it with my x-axis and my y-axis. So my x-axis is in L1, so I go second L1, and I put a comma. And my y-axis is L2, second L2. And I press enter. And what do you know? I now have, it says y equals ax plus b. Well, if that's the same as mx plus b, it's giving me these values. Let's get this out of the way here. It's saying a is 2.5. Well, that looks like about pretty close to what I had right there. And b is 29.56. That looks like about what I had right there. So it has given me the equation y equals mx plus b. And I could go, I'm going to come back to this in a minute. I could go and graph it. So I'm going to go second stat plot. I'm going to use, I'm going to do this. I'm going to turn all of these off. You can see that 1 is on, 2 is already off, and 3 is already off. But I'm just going to press 4. And plot's off, and I press enter. Now they're all off. So I'm going to go second stat plot, and they're all off. And I'm going to leave plot 1 because for whatever reason I wanted to keep that. And I'm going to use plot 2. Well, I'm going to turn it on. And the type I want to do is I want to do a scatter plot. And you can see by the thing that's blinking right there, well, that looks kind of like a scatter plot. And that's the graph that I want to do. So I'm going to press enter. And my x list was L1. So I'm going to go second 1, L1. And my y list was L2, second 2. I'll press enter. I'll use that mark, that's fine. I'll see if it'll calculate. I'll go zoom 9 for a step. And there's my scatter plot. And it looks very much like this scatter plot right over here. I can go trace, and I find out that my first number is age is 2, and the height is 34. And my next one, my age is 3, my height is 37. So I can even see that my data matches up right with that. And if I go back into my y equals, and I want to make just a regular old graph, not a stat graph, But I want to make a regular old graph, and I want that graph to have the equation y equals mx plus b. I want it to have this equation, this equation right here. So y equals plus 30. And now I'm going to go graph, and what do you know? It draws the line, and it looks like it goes through my points very closely. It looks like a line of best fit. But the last thing I want to point out is when I did that linear regression, I went stat, calc, 4, and I did L1, L2. So second 1, comma, second 2, enter, and I got those numbers. This number right here, R of 99.997, that is called my correlation. So my correlation is a positive 0.997. Now if you think about it for a minute, if I have a linear graph and I'm trying to match up two variables, if I have like 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and this was 1 and that was 1 and this was 2 and that was 2, 3, 3, 4, 4, 5, 5, I would have a perfectly straight line. And that perfectly straight line would have a slope, rise over run, of 1. Now it's also possible I could have a negative correlation. That was a perfectly straight line. And that would have a slope of -1. So in this one here, I'd have all my dots going there as a negative strong correlation. And in this one here, I have a positive strong linear correlation. If I had dots that were like just kind of like all over the place, and it wasn't linear, and they wasn't very strong, that would have a slope of 0. So the correlation, this number here, this number R right here, is giving you a number for how strong your correlation is. So it goes like this. Here's positive 1. Let's make it look like a 1. Here's -1. Here's 0. This is the strongest negative correlation you can possibly have. And this is the strongest positive correlation you can possibly have. At 0, it is the weakest correlation of all. So by having a number like 0.997, that is telling you if R is equal to 0.997, that is telling you it is a very strong positive correlation. So your calculator is going to help you find that like super quick as long as you know how to enter in the data properly.